Okay, hello and welcome to our discussion on integrated rate law. I just want to review where we are with kinetics and rate laws in general. Remember that rate laws depend on the data you've got. You measure how rate changes and as concentration change, you're looking at using differential rate law or rate equations. If you're measuring concentration as a function of time, we're going to be looking at through integrated rate law. So um, integrated rate law expresses concentration as a function of time. So instead of changing initial concentrations and using multiple different experiments to see rate, we're doing one experiment and measuring concentrations change over time. And this is just an example of what that graph looks like. It's not too different from what we see in the Pogmelon reaction rates, where we see concentration over time. This one happens to be a straight line, and we'll explain why in a future slide. We need to discuss first order integrated rate law first. This is kind of the big featured rate law. We're also going to look at second order and zero order. In integrated rate law, it's a little bit more challenging to look at the various different orders of reaction. So we focus on zero, first, and second order because they have relatively tidy graphing and trends. So what we need to know first is the equation that describes the integrated rate law for first order reactions, and that is the natural log of the original concentration divided by final concentration is equal to our rate constant, the same as it is for differential rate law, times time. This is not temperature. Leave temperature out on the boat with thermo. Um, we will also see it written thusly. This is just an adaptation of the same formula, and down here, this is the one that appears in the AP charts. They're all the same formula, adapted different ways for different points of view. What we need to know about integrated rate law is that this equation is true for first order reactions, but also that if we ever graph a first order reaction, we would see, if concentration versus time, we would see a nice curve. However, if we graph the natural log of concentration versus time, we get a nice straight line with a negative slope. And because of that, this is what we call the naughty-Katie formula. It's a silly name for not T-Katie. Well, not that it really matters to us a whole lot, but it's a way to remember what the formula applies to first order reactions, I guess. But the plot of natural log of concentration versus time gives a straight line in a first order reaction, where the slope is negative of your rate constant. So remember, your rate constant can't be negative. It can be really small, but it can't be negative. So this slope that we see in the natural log versus time graph is equal to the negative of your rate constant in a first order reaction only. Zero and second order, we look at it with a different graph in mind, and we'll talk about that on a future slide as well. So this is a question that asks us to determine concentration. So it's a first order conversion, so it tells us in the question it's first order, cyclopropane to propylene, and there's a rate constant of that value. If the initial concentration of cyclopropane is that value at 400 Celsius, what will the concentration be 24 hours after the reaction begins? Now it's important to remember what our equation says for a first order reaction. It's concentrations and time and the rate constant. And the time needs to match between your rate constant K and the time values in your equation. So we need to convert our hours down to seconds. And so this first step, I've done that. And then I've written a version of the formula here that we need to adapt to solve for the final concentration. And so what we're going to do is put each side of the equation to the power of E, or e to the power of each side of this equation, pardon me, to get rid of the natural log, and that gets us to that, which we can then simplify and solve for our final concentration. So it ends up being original concentration divided by e to the power of our rate constant times time. And that gives us a final concentration of 9.05 10 to the negative 3 molar. Now we can also look at first order reactions through the eyes of radioactive decay, because radioactive decay is a first order process. Now, a lot of AP Chem that's first order will use radioactive decay or first order decay to describe a chemical reaction, but we can also look at it through number of particles. So if we're looking at the rate of decay of a particle, we would look number of particles change over a period of time, also equal to the rate constant times the number of particles, where n is the number of particles, yes. So this is just a derived version of that same equation we did before. Half-life is the length of time required for the concentration of a reactant to decrease to half its initial value, or half-life is 0.693 divided by K. where people often ask where 0.693 comes from. 0.693 is a natural log of 2, which is consistent. It's half-life we're talking about. We could go backwards and rearrange the equation to put it back in, but essentially what you need to know is 0.693 is the natural log of 2. This graphic is of a chemical reaction. This is not a chemical reaction, a nuclear reaction of strontium decaying, strontium-90 decaying, and the half-life being 28.8 years, and then 4 half-lives. Not different from a chemical reaction that has a similar decay pattern. We've already talked about large K reactions being fast and small K reactions being slow. We can also throw half-life into that. A large K fast reaction has a short half-life. A small K slow reaction has a long half-life. Just an association perhaps could be used in a question. Here's a chemical reaction of a first order. This is decomposition of dinitrogen pentoxide, and we can just see exactly the same pattern of half-life. This is in seconds. Per 100 seconds, we see half decay of the dinitrogen pentoxide. So here's a question. Decomposition of SO2Cl and chlorine gas is a first order reaction with this K value at 320 Celsius. Temperature is not important for the process, although people ask. It is a fact, and it does describe this K, but it isn't part of the equation. Determine half-life. When we know K, half-life is a short step. It's simply plugging into the half-life equation 0.693. This is a typo, I apologize. 0.693 divided by K yields the half-life. There we have the operation, and then there's the answer. This would be in seconds. You know, it depends on the type of question we get out of this, and it would usually guide us to the proper unit. Since our K value is given in seconds, it's appropriate to respond with half-life in seconds also. But you could go to minutes or hours if you needed. A little more in-depth question. The decomposition of dinitrogen pentoxide dissolved in carbon tetrachloride is first order. The chemical changes that process. At that certain temperature, the reaction was begun with an initial concentration of 1, so that would be our A naught. After 3 hours, the concentration had decreased to 1.21 times 10 negative 3. That would be our A sub T. After a certain time, 3 hours, T. What is the half-life expressed in minutes? Always read your question. If it directs you towards a unit, please be very careful that you hit that unit in your answer. So here's again the naughty KD formula, the first order reaction formula, where we need to solve for K, that when you can then use K to solve for half-life. And you can combine equations if you want to, but not necessary. You can just plug in, let's find our K value with this operation. That yields 0.073 minutes, inverse of minute. For our K value, and again, first order, so it's 1 less than our overall reaction order, which would mean 1 over our time is our unit for K, which is consistent with this value. Then we would plug that into our half-life equation and get 18.6 minutes. Please pause and look at that math if you need to. A couple more advanced half-life questions, and this is a radioactive decay, so this isn't common on the AP test, but they can appear, not so much anymore, but we may see them in our practice. Radioactive decay of thallium-206 to lead-206 has a half-life of 4.20 minutes. Starting with that number of atoms of thallium, calculate the number of such atoms left after that time. Keep in mind that for this, we're going to replace our concentration with a number of atoms or a number of particles. So here's our half-life equation. There's our 4.2 minutes. We're going to find our K value. We're going to find our N sub T from this process. Our K value is this, then we can plug that into the naughty KD formula with N replacing A. And there's our original number of particles divided by our unknown we're solving for here. Our calculated K value, our time that's elapsed in minutes, so our number of particles is going to be 4.89 10 to the 19th atoms. And again, you're left with this value inside of a natural log, and so if you use e to the power of, you can get rid of that and make it a little simpler algebra. But you can see the process where we need to solve for the n. Another question is phrased a little differently. We have yttrium-90 found to have an activity of 9.8 10 to the 5th disintegrations per minute. So this is how many particles disintegrate in a minute. So it's actually kind of a rate. of disintegration. But we can use it the same way for number of particles decaying in a minute originally and number of particles decaying in a minute at time t. At 1 p.m. on December 3rd, 1995, at 2:15 on December 17th, so the elapsed time would be the 3rd to the 17th is 14 days and 1 hour and 15 minutes. Its activity was redetermined and found to be 2.6 times 10 to the 4th disintegrations per minute. So here's our initial rate, 9.8 10 to the 5th, and our final rate, 2.6 10 to the 4th. And because those are both rates with the same units, we can plug them into this association and still have it proportional to our time. So we're going to calculate half-life, T1 half. So we've got to do a little bit of work to find a K value, and we can do it still with the naughty KD formula. So this is 14 days and 1 1/4 hours. This is how many hours it is in decimals, which we'll need to work with. We can't really work with this. So then we can plug everything into naughty KD formula. There's our two values. Natural log of those will give us the time times our K value that we need to calculate half-life. And this math is pretty straightforward. You get 0.011 hour, inverse of an hour. And then we'll plug this value into this. Okay? And that gives us a half-life of 0.693 divided by that value. And then our half-life is 63 hours. 2 sig figs because we were dealing with 2 sig figs from the beginning. Students often ask, what is K? K is just a number that makes an equation true. So don't get caught up in the fact that these units appear odd. It's not too different from when we saw hertz in the cycles per second of a wave. It's kind of similar in the inverse of a time frame. So let's look on to the next slide here. We have a second order integrated rate law, which is just given by this equation. And our equation that makes this true with the second order rate law in terms of time and our constant is going to be the inverse of the final concentration minus the inverse of the initial concentration. If we plot the inverse of concentration versus time in a second order integrated or second order reaction, we will have a straight line slope equal to a K, our rate constant. It's not negative K like in first order, it's just K. And the reason for that is when you plot the second order inverse, you're going to get a slope up and to the right. But that slope is equal to K. So this is going to be 1 over concentration versus time. Okay, whereas in first order, we had a downward sloping line. So nevertheless, when you have a second order reaction and you graph all three possible curves, we have concentration, we have natural log of concentration, and we have inverse of concentration, we will get curved lines for these, and we will get a nice straight line for the inverse. And that would prove to us graphically with data that this is a second order reaction if we had no other information. So this is what it looks like when we have a a second order reaction natural log plot. Since it's second order, we don't get a straight line with a natural log plot, but with an inverse plot, we do get a nice positive slope straight line. This gives us evidence that this reaction is indeed a second order reaction. Now, it doesn't mean that there's only 0 first and second order that we see these plots. These are what are tested in chemistry commonly. There is possibility of other types of order reactions, but we won't work with them. 0th order rate law is essentially rate is going to be equal to your rate constant, where the rate constant times in 0th order, concentration final minus concentration initial is equal to the negative of the rate constant times time. Essentially, this means that our rate is independent of the concentration changing. It's going to be what it is. Your concentration is going to change at its own rate regardless of what you do. Or sorry, our reaction is going to precede it at its own rate regardless of what happens to concentration. So a plot of concentration versus time produces a straight line with the slope of negative K. So, not too dissimilar from what we saw from a natural log plot of a first order, we get a negative slope with a 0 order. So if we have a 0 order reaction, when we plot all three, concentration versus time, natural log of concentration versus time, and inverse of concentration versus time, where this is time. For a first order, we would get a nice straight line down to the right. For a first order, we would get a curve. And for a second order, we would also get a curve. So we would be able to prove that this is a zero order reaction based on the evidence of our plot. So that's that. Finally, this is a summary of the zero, first, and second order reactions, their associated equations, what to look for in the curves, and then when you would get a straight line plot, the integrated rate law formula versus the differential rate law equation. Now these are things you already. This is inference based. These are going to these two are going to be provided to you on the AP exam, not the zeroth order, but the first and second order. Relative concentrations over time and the impact of the values. So if you notice, this is probably most revealing. The zero order, no matter what you do to concentration, rate stays the same. And then first order, you see that it's proportional to concentration change. You have a direct impact on rate, and then you have an exponential impact in second order. Then we have half-life. This isn't something we really need to focus on at all. This is the only half-life equation we'll really use. And then we have the units of the rate constant. And that's that. The next video we focus on will look at reaction mechanisms. Make sure that you're taking high quality notes when you watch these videos, and we'll see you on the next one.